Hello everyone, welcome back to the channel. In this lesson, we are going to solve a problem based on prime numbers. We have to check whether the input number is a prime number or not. Let us understand what is a prime number. A prime number is a whole number which is greater than 1 and has exactly two factors, 1 and itself. So here are the examples of prime numbers that are only divisible by 1 and the number itself. As per the definition, we have understood that if the input number is num, it is only divisible by 1 and the number itself. So we have to exclude these two numbers and have to generate the sequence that remains within this range, and we'll divide this number num with those sequence of numbers to check whether they can evenly divide num or not. If they can, then in that case num is not going to be a prime number. Take an example of 7. We will generate the sequence of numbers starting from 2 to 6. So all these numbers, that is 2, 3, 4, 5 and 6, will divide num one by one, and we'll check whether they can evenly divide num. And how we can verify that? We can verify that with the help of modulus operator. So let's say the first number in the sequence is 2. We will check whether num mod 2 returns the remainder which is equivalent to 0. If it returns, then 7 is divisible by 2. But in this case, it is not. We will repeat this step with number 3, 4, 5 and 6. And the finding is none of these number can evenly divide num because we are not getting any remainder which is equivalent to 0. And therefore, 7 will be a prime number. So this is the logic we will use in our solution, and this is going to be the first solution. Later on I will discuss little better solution. So let us start writing the code and understand how the Python code will look like. The very first thing is we have to accept the user input. We will say that int input enter any number. So whatever the input is given by the user, we will transform it into the integer because the input will be in the string form. And I will define a variable is prime, which I will set to true initially, stating that the number is prime. Now the next thing is we have to generate the sequence of number, and for that I will be using the range function, and we'll say that for I in range start from 2 to num. So num is going to act as the upper limit, and therefore we will get the number starting from 2 till the num value. Okay, if it is 7, then the number generated will be 2 to 6, and I will show you that in a moment. So let us say that I want to see the value of I, and will update end to comma and space. Let us execute this code. I'm going to pass 7, and you can see that we have got the sequence of number starting from 2 to the upper limit which is excluded, and therefore we have got numbers 2 to 6. And we will be using this code to check whether the input number is a prime number or not. And now we will check if num is evenly divisible by the sequence of number which is going to act as I is equals to 0. So over here we are checking the remainder. So we are dividing num by I, and if the remainder is equals to 0, then it is a number which can evenly divide the num, and therefore num is not going to be a prime number. And therefore we will set is prime to false, and will break the execution of the for loop. So iteration will be stopped, and we will come out of for loop, and over here we will check if is prime. If it is, then we will say that the number that user has input is num is a prime number. If it is not the case, that is if the value of is prime is false, then we will say that the input number is not a prime number. Let us execute this code. I'm going to pass 12, and 12 is not a prime number, and therefore it says that 12 is not a prime number. I'm going to pass 7. It says that 7 is a prime number. Although we have solved this exercise, this is the solution, but this solution is not giving us great performance. Why? Because this is going to iterate at least n minus 2 times. How come it is going to iterate n minus 2 times? Consider that you have got a number 7. Then in order to check whether it is a prime number or not, you will start from 2. You will check whether 7 mod 2 gives you remainder equivalent to 0 or not. Then you will test with 3, then 4, then 5, and then 6. So number of iterations we are getting over here are 5. So this states that we have n minus 2 iterations. If it is a non-prime number, then obviously you would get lesser number of iterations, but consider that you are going to test the prime number which is of at least a 6-digit or 7-digit number, then you can think how many iterations it will do to check whether that number is prime or not, and we want lesser number of iterations to get great performance. So what we will do in this solution is we will find out the 1.5 of this number. So 1.5 of this number is 3.5. So we will extract the integer part of this number, which is 3, and we will set it as a upper limit. Now we know that when we use the range function, the upper limit is always excluded. So we will have to say that we want the sequence of numbers starting from 2 to 4. Therefore, it will generate sequence 2 and 3. If number is evenly divisible by 2 or 3, then it is not a prime number. Otherwise, it will be a prime number. Now over here you can see we have reduced the number of iteration by 50%, right? So we will use this logic to solve the problem. And now I'm going to copy this code and we'll say that this is a solution 2. We'll paste this code over here, and now we will say that we want to divide this number by 2, and I'm using float division operator, and it will just give us the integer part, and then we will add 1 to it. Okay, and now let us execute this code. I'm going to pass 12. It says that 12 is not a prime number. Let us test 7 is a prime number. Let us test 13 is again a prime number. Although we have enhanced the performance of this code slightly, but this is not the optimal solution. Over here, I have calculated the upper limit as 1.5 of the input number plus 1, but this is not going to resolve the concern of the performance. Now what I will do is I will set upper limit to the square root of the number. So in order to calculate the square root of the number, I will be using the exponent operator, and 0.5 means I want to calculate the square root. And once the square root is calculated, I will transform it into the integer, and then I will add 1 to the value. So what it does, consider the example of 13, then you will understand it. Consider the example of 13. The square root of the 13 is 3.6. When I will typecast this floating point result to integer, I will get the lower limit, which is going to be 3, and then I will add it to 1. This is going to be the upper limit for the range function, and then this would be the start position, and this is going to be the upper limit, and therefore the number that we will get would be 2 and 3. Now we will divide 13 by 2 to check whether it is evenly divisible, and then we will divide it by 3 to check whether it is evenly divisible or not. So now we know that 13 is a prime number, then it is not going to get divided by either of these. I will talk about another example to connect you with what I am talking about. 14 has a square root of 3.74, and once it is typecast to integer, we will get 3. 3 plus 1 is going to be the upper limit for range, and we will get sequence starting from 2 to 4. That is 2 and 3 will be the sequence of number generated by the range function. Now we will divide 14 by 2 to check whether it is evenly divisible. And how we will check that? We will use the remainder operator, that is modulus operator. We will check 14 modulus 2 is equals to 0. Yes, it is, because 14 is divisible by 2. And right at that position, we will interrupt the execution of the for loop. Over here, you can see that 14 is evenly divisible by 2 and returns 7. This justifies that 14 is also divisible by 7. The divisor 2 is less than the square root value of 14, which is 3.74, and the divisor 7 is above the square root value of 14. From this, it is justified that if a number has a divisor greater than its square root, it must also have a divisor less than its square root. So what that means is, if 14 is divisible by the number which is smaller than its square root, then we will definitely have its divisor, which is greater than its square root value. And that's the logic we are going to apply in our solution, and it will drastically change the performance of the code. Let's remove everything I have written, and I'm going to copy this code, and this is going to be the third solution to this problem. Now I will paste this code. The only change that I have to make over here is to calculate the square root of num, and then I will typecast it into the integer, and then we will execute this code. Let us pass 13. It says that it is a prime number. I'm going to pass 17. It says that it is a prime number. I will pass 23, is again a prime number. If I pass 30, it says that it is not a prime number. Pass 32 is not a prime number. Once more, we will test 33, and it says that it is not a prime number. See, we have discussed 3 different solutions, and every solution is working perfectly fine. However, the third solution is the optimal solution.